All right, let's get started with our second day. Yesterday it was more or less on time that we finished what I've prepared. Let's see how it works out today. Quite a few different topics to what we've had yesterday. Let me skip forward here. Over our program, the introduction, you have the link to it all, to the overview. Yeah, quant finance, ChatGPT is something that we have made, check. A little bit of a discussion, check. A little bit of an overview, simple examples, a little bit of an exercise that we more or less together solved. Right? Advanced financial examples, credit score prediction. We have seen that decision trees sometimes are pretty good at doing seemingly complex stuff. Right? I think I have repeated the execution, but maybe I have on the way changed something with the model, so I tried a few configurations. I'm sure I've seen before with the deep neural network something like 90% plus, but here either the training or the architecture, something here is missing, I don't know. But feel free to play around with it. You have the code. That's the beauty of Jupyter Notebook. You download it, you run it, and then you can adjust it to your liking, right? So let me maybe save this. We won't need this anymore. This is also something for later. And also financial data APIs. I mean, this whole exercise with regard to AI in general, machine learning in particular, applied to finance, lives and dies with the availability of data. So most of the data sets that we've used have been from the EOD historical data API. This one example here with the credit scores, this has been from Kaggle, what I was showing you, or have provided the link as well, right? So now, speaking of data and the availability of data, that's kind of like my bridge. So we have, of course, historical data, but it is, even if it's well more than 5 years ago, well more than 10 years ago, and much more than 15, 20 years ago, it's still, for many applications, not enough data, right? Therefore, not only to generate nice pictures of whatever, of your dream car or something else, we can use other methods to generate stuff. And the stuff here in our case is financial time series data. And that's the topic that I want to get started with here. Generating financial data. Noisy data will be my first pretty simple example, but straightforward. Simulated data, the Vasichek model, originally in the 70s introduced for pricing of rates. Products and the modeling first of rates and then the pricing of products on the rates, and then the bit more modern approach of GANs, generative adversarial nets here, so that we can then apply with one of the methods reinforcement learning for delta hedging and see how A, reinforcement learning works, and B, see the benefits of having such an approach available, that we say, well, we are not limited to one time series, right? So what we have done before was basically all based on a single time series when we have been working with the time series, right? We could choose maybe different symbols with different time series, but when we analyzed, let's say, Netflix stock price data, it was just this one history, because there is just one history, right? So that's simply not enough. In general, we could then maybe move to intraday data or to tick data, but in the end, this doesn't solve the problem. It just gives us more data, but the data is fixed as it is. Yeah, then we turn our attention from the structured data, from numerical data, to the basics of NLP, natural language processing, where I have prepared a couple of examples. I would say this is not over-structured, over-organized, that part. I've tried to provide a collection to show what you can do with Python as a basis for what is to follow, a little bit more with than NLTK, which is at the core there, what tokenization is about, a little bit of summarization, If we like, we could go and do a little exercise with a text that is of interest to you. Then, with all the basics now covered, we might turn our attention here in more or less the final part to the large language models with which we got started and which I want to use here and there again, right? And the final example will be about the API of GPT, the OpenAI API, which provides access to more than just GPT-4, let's say. So this shall then close the circle to what we got started with, right? So the notebook number should basically be clear because we got started. Let me shut down this kernel here because we ended with the 04, and here in 05 I have the next stuff. So simulating financial time series data, and there are two approaches in this Jupyter Notebook. I said it before, the one is simply to add noise, white noise, normally distributed noise to existing time series data. And there's one saying, and I think this is inspired by the saying, they say, well, we need to distinguish the signal from the noise. So here in this situation, we interpret then maybe the underlying historical time series as the signal itself and add noise on top of the signal. Of course, in finance, people usually say, well, not every movement that we observe in the market is really a signal. There might be whatever happening in the markets, people driven, etc. So here I define for myself, for us to work, signal and noise a little bit differently. So all this is here based on environments that this is now part or will be part of my book about reinforcement learning for finance. Therefore, it is all presented in Python class form and with an API that is appropriate to be applied in the context of reinforcement learning. Of course, this could be done in many different ways, but that's now the background because the next example is also based on reinforcement learning as outlined before. So let me get started here with some imports. You might wonder, what is action space? Yeah, this is a simple helper class. I see this is just 3 lines, and I use it in the noisy data class here as, how shall I say, as a helper to make the API consistent with the OpenAI GIM API. So many AIs, OpenAI API, more A's and I's than anything else. I here use a random number generator. I'm still more or less, when I type stuff out, I'm still with what they call these days legacy random number generator, so np.random.whatever. Right, these days the standard should be to use one from random and instantiate a random number generator object, here the default one, and then use this one. But I've made a couple of tests when they introduced it. It is faster. So I haven't checked now whether the convergence in the moments is faster or whatnot, but the generation of, let's say, 1 million, 1 billion random numbers is faster with the new one as compared to the old one. And they claim that the algorithms that are used in the new version are better as well. I would trust that, right? And better means like, right, when you have an idea of like an area which you want to fill with random numbers, and you would say, well, this is more evenly distributed, right? Because the uniform number generator, that's usually at the core of everything else, right? So here the URL can be as it is if you have the whole repository on your machine, but I replaced it here what is on the server so that it might be executed also in a different place, because they are now all there. So in the first step, you see, so there's now a couple of steps. This is also now a bit driven by how I presented in the chapter in the book, right? First the init method, which takes a couple of parameters as input. Minimum accuracy here in this context is for an agent that predicts upwards, downwards movement. So we can call this maybe a prediction game for the reinforcement learning agent, and it requires a minimum accuracy for the agent to be able to go forward, right? When it's worse than kind of like tossing a coin, where's the point like in moving forward? But this can be adjusted, and you can play with that. Sometimes it's nice to have a relatively high bar from the beginning. Sometimes you want to let it learn first and then improve later. So I have seen many use cases that react differently on this parameter. So noise true is the default, and noise standard deviation here 0.001. This might need to be adjusted given the time series that we use, right? So then symbol feature, number of features. This defines what is delivered, so to say, by this environment to the reinforcement learning agent. So I can, in this case, you might recall that we have 14 different time series in there. So as a basis, I can pick Goldman Sachs or Apple or Amazon, whatever is in there. Then I can decide on the feature whether this might be, for example, the price itself or the return. So we have seen already in the context of stock market prediction, with prices usually we won't get that far, right? And also from a algorithmic conceptual point of view, it's usually not advised to go with prices. Therefore, we take in general here the returns. But this can be anything else. So I'm here talking about something that is implemented as it is, but this whole construction has, of course, a couple of decisions that could have been made differently instead of left. Might have gone right. Then noise here is this flag, so I can simply provide the original time series as a special case. Standard deviation is stored as an instance attribute action space here for the consistency with the API. Minimum accuracy is stored, and then it gets the data here. That's an internal helper method for the URL, right? So I could now check all this, but I first want to build the whole class and then apply it, right? So the next method that is called here during the initialization is prepare data, and here this could be made well more complex. So I would say that's something like a minimum set here where we have the data itself for the symbol, then we add noise or we don't add noise, right? So we have the core, the benchmark case without noise always with us. Calculate the log return for the time series, calculate the or derive from the log returns the directional data. So here this is going with 1 and 0. I've commented on this that for example, what we have done with MLP regressor, MLP classifier, there it doesn't matter, but once you, for example, want to apply TensorFlow, it expects these binary labels to be 0, 1, whatever, with no negative values, as one example. Right? To a drop NA, here do the normalization. This is done here not according to Gaussian normalization. Here it's implemented as min-max normalization. So then in such a context, we typically do something like a reset of the environment to say, well, like ready, steady, go. Right? We reset everything to 0 when it makes sense, or to an appropriate initial value. Right? If we have noise true, then it will go back to prepare data, otherwise not. Right? Why is that the case? Yeah, this means that when noise is set to true, it will every time it will add different noise, so that the agent who is interacting with the environment will every time see a different time series. It reacts 1,000 times with it. It will see 1,000 different time series, which at the core are derived from the original one. Bar here is simply a counter, so to say. I start, that's a time series, I have a couple of things in the beginning that I can use, then I start at the initial bar, which is here the number of features, and then I go step by step by step by step, which means I move the environment bar by bar forward. Total reward is set to 0, so over time the agent receives a reward. So with regard to all these notions, etc., I have the slides in the slide deck for reference. This is also detailed, for example, in the book AI in Finance. I have, and in many other books as well, but among others in my book too. I've seen that already. And the last code line here, this gives the initial state. So for example, the canonical example to introduce reinforcement learning based on the OpenAI gym environment is the card pull game. And there we also have the situation that is replicated here, that whenever you initialize the environment, you will be confronted with something random. So you cannot say up front, well, the stock price always starts at 100 or whatever. This is the case when we work just with the time series itself, like we have done for supervised learning. This was one time series. We have derived the features, we have derived the labels, and then we have worked with it. So this was fixed, like put in stone. Here it changes all the time, apart from the case when I say, no, I don't want any noise. Right? Now the major method here in the environment is the step environment. So we have the environment, we have the state which describes the environment, and stepping means we move the environment from one state to the next. It's all now reinforcement learning language, right? And the first thing that the step method here checks is, given the action, and I have intentionally here left the word action. This could, depending on the use case, I said this could be used, for example, for a prediction game. This could be also called prediction. But in a reinforcement learning context, you would typically call what is happening here an action. So whatever this might mean. In a gaming context, move the bar to the left, move the bar to the right. This would be an action. Right? An action in a chess context would mean make a move. Right? Move the pawn, e2, e4, for example. This would be an action. So whatever it is an action. Here, even if it's just a prediction, it is nevertheless called an action, so to say. And it checks whether the action, in our case prediction, equals the direction. Right? So the reinforcement agent sees 5, 7, 17 historical data point, like in our prediction example from yesterday. And his task is to predict next day's market movement. The problem, more or less, is exactly the same that we have implemented yesterday with supervised learning on a static data set. Here, it's a little bit different. The agent goes over the time series, right? Like Einstein sitting on the light beam, right? So going over it, moving the environment forward. So here, the analogy has its problem. So for example, I mentioned this a few times now when I gave my CQF lecture. The subtitle is also about reinforcement learning for algorithmic trading. The subtitle there is From Playing Games to Algorithmic Trading. Right? So many things in this, at least from my experience, from my point of view, in the area of reinforcement learning is driven by this gaming context, right? We are here now in the financial context. Some expressions are leftovers, right? When I say given the prediction, the agent moves the environment one step forward, doesn't involve any impact on the environment. This is something which we need to be aware of here. This is one of the major drawbacks when we are dealing with finance. Here, in the way it is implemented, right, in a traditional financial way, where we would say the agent, who is so small that no matter what he does has no impact on prices on whatever, right? So we would think of a marginal agent, right? Of course, this might change when you want to do something like this and you are a hedge fund and you trade, right? Then liquidity plays a role. And for example, in terms of like optimal execution policies, reinforcement learning has been applied, because there it's exactly the problem. When I now, or the problem first, first things first, when I, for example, go short, this might further push down the price, right? Positive feedback, therefore optimal execution. Well, I need to size the positions correctly. I need the timing being correctly, appropriately, right? In order to not have a too large an impact. So here, moving forward just means I do the prediction, I get some reward, and then we go to the next state. This is nothing like open a door and now the door is open. No, the door is open no matter whether I'm on the outside or on the inside. It doesn't change the state here of the facility, whether I'm out or in. And similar here in this context. So we set here to true, otherwise to false, right? We are either correct or not. So we have the agent has done a correct prediction or not a correct prediction.
Would the reward matter if we change that to other?
If you change it to what?
If you put 2 or 3 or 4, does the value
No,
matter?
not on this level. So depending on what you want to implement, and when I showcase more advanced financial environments, so here these are starting ones, then what I do, for example, related to the discussion that we had yesterday, for example, you can give a reward which either completely or among others depends on the profit or loss. So here you would have a natural mechanism, right, to award for a high profit trade more makes sense, right, and to penalize a large long trade, right, where you miss out either on opportunity or you get simply decide incorrect. This can be adjusted. So reward design is a discipline that is, of course, really important here, but the way this is now presented doesn't, here it doesn't yet make really sense. Also, I'm not talking about the agent itself and what the goal is. It's very simple. He should try to predict as many directions correctly as possible. The same thing that we did with supervised learning yesterday, right? In other words, only the accuracy ratio is what counts. So, and he gets the exact feedback that he needs. Either I'm correct 1 or I'm wrong, then I get a 0. When I say I say this quite often. You might notice I mean the agent, right? Because we could play the game as well. We could also sit there, right? Have a look at the 5 previous observations and try to somehow come up with a prediction. So here, bar plus equals 1, this is technically now the moving forward in the environment, which simply sets the bar counter on the time series data 1 forward, 1 forward, 1 forward, right? So, and in that sense, the 4, 5, 7, 8 features, lags that we use, they move forward. The window moves forward as well. Calculate the accuracy here. Given the predictions, then we have the breaking conditions here. One thing is clear, once we reach the end of the data, we cannot play the game any further. So that's the first one here. Data is used up, done is set to true. Reward, in other cases, if we have data left and I get a positive reward, then done is false, so I can play further, right? In another case that we might want to check, so let's say we still have data left, but we have done an incorrect prediction, right? Then we would check, for example, for the accuracy. Right? Let's say we have had 5, 10 incorrect predictions in a row, then the accuracy is checked, but only after 15 rounds of predicting, because in the very beginning it will be like, one thing is wrong, the second, oh, I've lost. Right? So we wait a little bit, the grace period. 15 is also more or less arbitrary. I've been playing around with that also quite a bit, but this seems to make somehow sense around 15 to get started. Then I say done is true whenever the accuracy is lower. In the other case, if there might be some cases left, honestly, I don't know, it is set to false. The next state is now derived here based on the normalized data, and I return what is in line with the OpenAI gym environment. You get the state, you get a reward, then the bool value here for done, either yes or no, true or false. False here is that we don't do anything with truncation. This would be the fourth one. And there's also an info object, for example, when you work with a card pool environment, that's also always empty. In more complex environments, you might get additional information about whatever. So let's instantiate such an object, noisy data. Here I pick Apple, noise true, and I said it before, because this is now relatively, how shall I say? You might, depending on the instrument, I think that's a good way to put it, you might need to decide on a little bit of a higher noise value or a little bit lower, right? When you're dealing with a high volatile stock, this might be something else than like a slow-moving currency, which is more or less stable over long stretches, right? So instantiate this. What error do we get? Something with the data. Oh, whoa, this is a long traceback. Seems to be something with data set. Is this not the correct one? Typo. Nobody has noticed it's difficult. Simple, tiny character. What's missing? So this is how it looks once the environment is instantiated. We have gone through the elements, so a number of instance attributes are created, two methods are called. First get the data, then prepare the data, right? And here you might have noticed, or maybe not, with the exercise from yesterday with regard to the stock market prediction, we have done this just once. So we have created all the lag data points and then ended up from a, let's say, one-dimensional time series. We ended up with a matrix, right, with the features plus the labels, or labels features, depending on how you want to see it. Here we don't do this first and then provide it. Here we simply, again, move the bar forward and take the last four values looking backwards. These values look pretty, let me see. They look all pretty close to 1 somehow here. When I do another reset, this is what I want to show here. They're still pretty close to 1. Whenever I do a reset now with the noise argument set to true, I get different values for all the 4 state values, right? Now I do it with a bit more of a, this is pretty low noise, we would say. This is a bit more noise, right? 4 features, that's the same. Now the values are completely different here to the ones from before, and here also larger differences from the one reset to the other. I could now repeat this a couple of times or implement a loop, for example, but the message, I guess, it's clear. Doing a little bit of plotting. Here I do 5 plots every time I reset the environment, and now we know that this leads to new noise that is created, added to the original time series. And we have here then something that looks like this. I think I just plotted here from 2023. When I take this out, for example, and do it over the whole time series, we see here noise kind of nicely, right? But we don't see that much as compared to the to the zoom in, but maybe I do it nevertheless, because this also gives a good feeling, I would say, for the for the impact of the noise standard deviation that we assume, right? So this was exactly the wrong place. All right, so this is the zoom in version, and maybe we have this high level overview there as well. The alpha factor doesn't make it really better. But you see, the original time series, the whole, if I can call it structure or roughly form, maybe we can call it, stays the same, but around what we have had before, we now have this noise. So from the point of view of a reinforcement learning agent, it's basically every time it's a new time series that he is getting presented with, or that they are getting presented with without any gender nouns here, right? So maybe we have a female agent who tries to learn that. And so we can generate with this pretty simple approach, and simple in the sense of compared to an environment which would spit out basically just the fixed time series. The only thing that we do here more or less is to add this part where we add the noise to it, right? So that's basically it, right? So it's like in finance, I think finance people like to have that. I have come up with a model which does X, Y, that much better than the original one, but as a limiting case, I have the original one still included. So I don't know, like a stochastic volatility model of Heston has included, obviously, the Black-Scholes model, or the jump diffusion model has the Black-Scholes model included. So this is what I guess finance people like to have in general. Something new, but still the old is preserved as a limiting case. Speaking of finance models, and what we like to have there, right? The next one is really about Monte Carlo simulation. So the other one, I don't know, I call this also simulation, but this is simply adding noise. I wouldn't say if this is really simulation. For me, having done over years primarily Monte Carlo simulation with Python, applied to options, hedging, etc. Simulation means in general that we have really a simulated path based on a probably parsimonious stochastic model for the stock price. I mentioned a few. Maybe it's simple as geometric boundary motion, or it is jump diffusion, or it is stochastic volatility, or stochastic volatility jump diffusion, or you name it. And you can use them in some cases to derive closed form option prices, analytical formulas. In other cases, maybe you might need to do simulation all the time. So here, the simulation class, it's called now simulation. The other one was called noisy data. What has changed here? So self, symbol, feature, and number of features. We know now number of features just defines like how far we go back, like the number of features we had yesterday in supervised learning. Minimum accuracy by default set to 52.5. X0 now is the initial value of whatever this is. So it can be a short rate, interest rate, can be a stock, can be a FX, can be index, a bond. Depends on whether the model makes sense for the instrument, but we can interpret this quote unquote however we like. I'm not providing here now any proper interpretation. Before it was simple because we started, let's say, with the Apple stock price or Netflix or Goldman Sachs or whatever is in the model. Then we add noise. Here there is no direct relationship to what is happening in the real world. We are not having as input a time series, nor do we say, well, this is for a stock necessarily. It can be other stuff as well. So we can define start, end, and the number of periods. The minimum, I jumped over this, I guess, before. Start and periods. It was that we start at this date, we end at this date, and we want to have 500 in between. Again, with the time series from before, without further adjustments, it always takes the original time series and adds noise to it. We could also, in that environment, say, well, I have parameters which allow me to slice out of the original data set, for example. Now the parameters for the Vasichek model. Maybe that's a good time in between, like, to go. There's another question I thought would be a good starting point, but let's do now a proper thing. Explain the Vasichek model for interest rates. The Vasichek model is a mathematical model used to predict the movement and evolution of interest rate. It's a single factor. I don't know if I would say predict. It is a single factor short rate model that is based on market risk, time, and long-term equilibrium interest rate values, right? Here we see a couple of things. Instantaneous interest rates, so this is what we usually call short rate, right? Market risk factor. So we have usually just one factor, which is normally distributed. So it will be a standard Brownian motion. Mean reversion, that's a good thing, because this is, among others, one reason why I've chosen the Vasichek model, because it does not only allow me to do things like geometric Brownian motion with trends, right? It allows me also to model stuff that is mean reverting, which might make sense in certain cases, right? Equilibrium value model outlines the movement of an interest rate as a factor, applications widely used in evaluation of interest rate futures, etc. Limitations. Yeah, it's a pretty simple model. Provide the mathematics of the model. It is the SDE. And here we see it. Right? The marginal increment of the current short rate value is kappa times theta minus r, the current rate, times the marginal increment in time plus the volatility factor times the marginal increment of the Brownian motion, right? Or Wiener process for us from Europe. Wiener process, right? The SDE can be rearranged, and it provides even a solution here to the model, or at least I don't want to dive into this. I was just after here the representation, right? So, and this part here in front makes sure here, because we subtract the current short rate, makes sure that we can model mean reversion. But we don't need to model mean reversion, it's just an option. So we can do some trending stuff, can do high volatility, low volatility, or mean reverting stuff. So it gives us quite a bit of flexibility. It's not the most complex one, but I think for such an environment that we are implementing here, that's indeed kind of a good starting point. So start-end periods, I was arguing about this. So here we have the boundary condition for the stochastic differential equation. That's the starting point. So we have an initial boundary condition, kappa, theta, sigma. These are the ones that were shown here, right? So we have kappa, theta, and sigma, right? Minimum accuracy, same reasoning as before. We require a minimum hurdle accuracy score in order for the agent to be allowed to play further, right? Normalize, true or not true, so this is a Boolean, right? And new means here something similar to the noise flag from before. So new means whether we want to re-simulate all the time. So it can be the case that I say, well, give me one simulated time series and I want to train the agent on that one time series over 1,000 episodes. Or I say, well, with new here, I say, well, every time over 1,000 time series, I want to get another simulated path. So, like before with do we have noise or not, and here is do we have new simulations or not. Simulate data replaces now the get data, so we need to work, or the machine needs to work here. And you see all these comments here, they are from my book. So this will be the callouts of the code in the O'Reilly books, ASCII Doctor. I thought I would have deleted them all, but obviously I haven't, right? Because here without any footnote, it doesn't make sense, right? Import math, think is self-explaining, we need it here and there. The class simulation from before, here with the init method, the only thing that was in there is now enhanced, augmented by simulate data, which replaces again the get data from before, and that's now an implementation for the simulation based on a discretization Euler scheme, discretization of the Vasichek model. In this case, we don't take care really whether it should be mean rewording or whatnot. This is later decided based on the parameters, obviously, right? Once we have done the simulation, I return here, or I instantiate, it's not returning, I instantiate an instance attribute which in a data frame form has now the single simulated path. So I'm not simulating 1,000 paths, what you often do, or 100,000 or 1,000,000 for option pricing. It's just one path. And if we redo this or not, this is decided based on the flag new. So the next step after we have that is to prepare the data. And the data preparation now is more or less the same as before. Not exactly the same, but more or less the same, meaning that we have the data stored in data as before. We calculate as a first step here the log return, do our trop NA, then we do normalization of the data here if the flag is set to true. In other cases, I simply create a copy of the original series, because later on I will reference in any case the data underscore object. Here self data R is used to derive the direction, nothing new here. And sometimes I like to have this as integers. So that's already, if you like, the data. And as they say, the rest is the same. The rest is history. And history in the sense of that what is coming now here is not different basically from what we have been doing before.
For that method, should we import TensorFlow at random or comment out?
Yeah, I could comment out this whole thing. I think this is not even used here, right? So, you see, I've taken this from another context. But you're right. I was just thinking, so why didn't throw me an error, right? Import error. Yeah, because I never called seed here. But you can do this, of course, right? Sorry?
No, it's me. It's usually me.
Yeah. So doing the reset, of course, I now have some different names, but overall it is like it is, right? So the step method, again, as before, once we have the data, once we have our features and everything else, the rest now is the same. So there's nothing really new about this. Therefore, I don't need to spend that much time reasoning behind accuracy, and here if, elif, else, exactly the same as before. So now this here, the symbol is just a symbol, right? So just to give it a name. As argued before, we are not having an original data set from which we take statistics or even the whole time series. This is just to have a name here available. And what I do here, so after I have deleted this, we have three different cases to get started with. There is what I call here the base case. Let's have a look. So all the start, end dates, and periods values here are the same. Also the initial starting values, they're all set to 1. Kappa is set to 1. From theta, you see they are on top of each other. This is now changing. So here theta, which is, when we have a quick look, what did I have in perplexity? Theta, this is what is called the long-term equilibrium level, mean interest rate. We are now not dealing with interest rate. I simply say this is euro US dollar. That's my freedom here. That's the long-term level. So this is supposed to be trending, let's say, a little bit. Long-term level 1.1. This a bit more. And this not at all. So this would be the case for mean reversion, and this would be the case for trend. The sigma value is the same, and normalized true is also the same. So you see the only difference that I make here is with regard to the theta value. In the first case, lightly trending. No, it's not the only one. I was a little bit too fast here, but let me argue about theta. Slight trend, more trend, and no trend, meaning mean reversion. Here I have set sigma to 0 as well. So in the base case, it's even deterministic. What is the, I haven't imported. Random, maybe I've deleted this later on. Having now created 3 different environments, we can compare our cases, and I would say these are the canonical cases. I have either something that goes straight up. It's a little bit the boring case. It doesn't take long for a reinforcement learning agent to recognize this. Here we have this stronger trending one, and the other one. So meaning that we have a trend doesn't guarantee that we end up at the long-term trend in the end. It just says it's trending towards this. But for sure, when we, where do I have it? The trend, that one. That is the mean reverting one. I want to have the, exactly that one with a 2. This can also be set instead of strongly trending upwards. This could also be something that strongly is trending downwards, right? Where we have, on average, in the long run, a drop of 50%. Of course, this is all on average. Still, we have the randomness, and the randomness is set here to a relatively low level. I can, instead of just getting the 0.5, so long-term level, I can here go with a much higher volatility, and then you see now how this looks like when I set this to a very small value, like 0.1. It looks almost like a deterministic phenomenon that we observe, but it's still a few kinks here and there. Yeah, this is what it gives us, not the whole world in finance that might be of interest, but at least, as I said before, maybe a bit of a starting point. So let me go with the standard ones. Right. So what else do we have here? Now we have something where we go with the returns values for lags, start 2023 and 2028, 500 periods, minimum accuracy 0.6, 1.25, theta 2, sigma 0.15, normalized, new, true. Why do I do this? Just to show you here a couple of plots. All of them are obviously in the beginning increasing rapidly and then getting flatter and flatter, and we have quite a bit of volatility. With such a chart, changing sigma from 15% to 5%, you see immediately the effect. 4, 10 plots. This was 15%. Right. When I set kappa instead of 1.25 to 0.25, you see this is not that strongly trending anymore, right? It's like somehow, or in other words, it would take much longer, right, to get the trending effect that we have seen before. Or when I would set kappa to 3.25, it would go even steeper up, and then you see it's more or less flattening out, meaning that it really quickly changes here the long-term level of 2, and from that point on we could say this is then mean reverting, because it's on the long-term level and it's just oscillating around that. So what makes sense for your application, for whatever, this needs to be decided here. This is just technical illustration. Maybe let me get back to the original parameterization. Right, so here we could go with the DQL learning agent. I have skipped that part, so I leave that out. The final one that we have here is, I think this is not necessary anymore. So two simple options, where we can either add noise or we can simulate. When we could now have one more option, and when you have seen it on the slides here. I have seen my blue book, Derivatives Analytics with Python. What is done in that book, and a lot of time and many pages is spent on this topic, is the calibration of models, right? So when we say, well, indeed, now we are interested in Apple stock price and want to simulate the Apple stock price with such a method, what are good parameters to choose, right? This is then where calibration comes into play, where you observe liquidly traded options in the market. You take the prices as given, and then you calibrate the single parameters that we have here, kappa, theta, sigma. You calibrate these parameters in a way so that the mean squared error, root mean squared error, whatever your success measure is, your yardstick is minimized. So again, in my blue book, there's quite a bunch of material for this particular topic. So I was thinking whether I should include something into the new O'Reilly book, but this would have been too long a detour. Maybe as an appendix or something, but it doesn't fit in the flow, right? So to say what are our option prices, how do this is a little bit more involved, basically, right? Yeah, two options, and both options allow us to generate unlimited data. Now we are in a situation which can be, at least to some extent, compared to chess and Go, where a machine can play an unlimited number of games. We can now here play an unlimited number of prediction games or hedging games, what I want to dive into, or anything else that is finance related, right? So there was the...
Do like jumps or something like that in the middle of it, you just use a different model whenever you're setting up the simulation?
Yeah, this is what I was saying. It's just this one part where the simulation takes place. Like before, where I said this is just one part where I add noise to it. Here's this one part where I define what is relevant, meaning the discretization for the stochastic differential equation. If I choose another model, I need, of course, other parameters to be input, but this should be a pretty straightforward exercise. To be honest, I haven't done it with, I don't know, Heston, stochastic volatility or whatnot. So far, with everything I've been doing in this context, I have done it for the Vasichek model, because when I did it for the first time, I thought this would be a simple enough model, which nevertheless gives us, as shown, as illustrated, enough wiggle room and enough options to go about this, right? So maybe in the meantime, I should somehow also get back every once in a while to the slides, because for some stuff I have financial data, what has been. Here, there are my subtitles, right? Financial data APIs can tell us what has been in the past, right? And the generating data part now, what could have been or what could be in the future, right? So that's the hypothetical part here. So generating data, I have nothing for the noise part, nor for the simulation part, but for the GAN part I have here, and there are, didn't I add here I thought I would have added it's strange, the links. I was actually sure I would have bet 50 US that I've added the links behind it. But you have the links to the papers anyways in the first Jupyter Notebook. There is the GAN link, and what is the other? They haven't provided the time GAN link, right? But at least the GAN link is in there. Right. So these two major papers, where I would say, well, the one is the GAN. This was the starting point, and then we have time GAN, which has become pretty popular. I'm not going to implement the time GAN because this has a couple of complexities that I want to avoid, even for the book, basically. But the results of that approach of this time series generative adversarial networks paper, there's also Python implementation available, which I don't really like. Surprisingly enough, when you have researchers coming up with nice algorithms, not always are they able to provide any decent Python code, to be honest. It's a bit sad, but I don't know. I don't want to complain because they provide the code after all, but it's not that easy to read, at least as far as I recall. Yeah, we have here the GAN, for example. Maybe let's do something that we have been doing before as well. Going here. Generative adversarial network. No, I need to right click, doesn't do the trick. I need to mark it. Plugins. Yeah, and in the end, when you think of what, I'm sorry, I cannot access, permission restriction. What is that? I don't know why this is not working. Here I can easily download it. Yeah, I need to do the reload. Now I have Clarity. Let's see whether Clarity has issues with it. So it's starting the summary. Well, Clarity doesn't have a problem with it, right? Paper introduced a new framework called GANs for estimating generative models. GANs consist of two models. A generative model that captures the data distribution and a discriminative model that estimates the probability that a sample came from the training data rather than the generative model. The training procedure involves a minimax to play a game where the generative model tries to maximize the probability of the discriminative model. Difficult words for me, making a mistake. The framework can be trained using backpropagation and does not require any Markov chains, etc. So we all know what these models are capable of, right? The Midjourney, DALL-E, and all these graphical things. I think that's pretty impressive, right? What they can do these days. The basic thing here is that we, and I think I have this quote at the start of the chapter, right? We can imagine. I don't know where the quote is originally from. I for sure have a source. Otherwise, I wouldn't use the quote. but they say this is like counterfeiting money, right? They are the criminals, right? They do some counterfeits, and then they go to the police. The police says, "Yeah, this is a counterfeit. This is not," and then they go back, right? And they improve the process since the police is getting more exposure to the counterfeit bills, right? Police is getting better. So the idea is that basically the generator and the discriminator are getting better and better by playing this two-player game, right? So therefore, it's not primarily the goal of the generative part, so to say, to be the winner in the game, right? To always outsmart the discriminator, right? They want to grow, if you like, they want to learn, they want to improve their skills more or less at the same time, simply speaking, right? So in the end, we have one model, the GAN, which consists of two models, right? And what we can do with it, I mentioned it before, is amazing, given that you can more or less here summarize it. Clarity has summarized it here, I don't know, in 20 lines, 20 short lines, and also given the fact that this is not too far back. This is just like 9 years back, and it took quite a while, as so often, until this really started flying, right? So with the GAN model, we can generate in the same vein as we did it before with the simulation, and with the noisy data, unlimited financial time series data, and data that we train on real data, right? The simulation approach, no relation, as I presented it, to any real world data points. Here we will train it on real world data and generate distributions or samples, I would say, where the part of the game is that the distribution shall be so close to the original distribution that the discriminator basically cannot distinguish anymore whether this is the right thing or some fake. Synthetic data is usually how it is called, right? So modern AI now applied to our finance context. The example that I'm going to show is a pretty simplified one in relation to what I was mentioning before, the time series GAN paper, right? So when I start this from scratch, so here we use indeed TensorFlow. Nothing special, pretty simple stuff actually. And the very simple beginning here is about something that is deterministic, right? So we have a function which is, you see it here, just a cubic function over the domain, closed domain, -2 to 500 data points. I do a standard scaling here, and this is what we get, right? Red is the real data. After normalization, we get the dashed blue line. So of course, this is for illustration purposes only, because that's a pretty simple case. There is, as we can see, there is no uncertainty whatsoever. It's just a deterministic function. It's a cubic function, period. Nothing more to say. But we can introduce, and I really get this here on the screen, completely the whole modeling architecture. I need to walk around. I'm sitting too long after my knee surgery. I can run again, but I can't sit too long. So the first is the generator. You see, that's absolutely straightforward. Right? Exactly the same what we have used before. It is a two-layer dense neural network. The output layer is with the linear activation function, we are interested in some estimation procedure. Floating point values, to keep it simple. Then we have the discriminator, and the discriminator, this is a classifier. I should say this is the real data or this is synthetic data, left or right, A or B, 1 or 0. Here we use sigmoid function, binary cross entropy, which is standard atom, and we are interested in the accuracy of the model. Then we have the GAN itself. So now we have like everything together and have the model here that is again three sequential models. Right? This is just hierarchical. I have the sequential model here where I add the generator first, then I have the discriminator added, and I compile this here also with binary cross entropy, because here that's the final thing here, right, is the classification approach. And the final three rows here are nothing else than the creation steps. Create the generator, create the discriminator, then create the GAN based on the generator and the discriminator. So you see, this is of course very, very simple when we talk about, I don't know, Midjourney and all these big things. Oh my goodness, we are light years away from these models, but the basic idea is reflected here. We have an estimation model for our use case, and we have the classification model, which should say it's correct or not, or it's real or synthetic. Then we have the GAN, which puts the two together in a row, and they are now getting trained more or less together. But what this means together, needs to be shown how we implement this, right? So creation here, that's a fast thing. This is nothing to do with training. This is simply function definition and instantiation of the sequential models here for TensorFlow. Going with the default random number generator, we now come to the second important part here. As usual, we will train such a model over a certain number of epochs or episodes, 100, 1,000, 50. Usually these models need to be trained over quite a large number of epochs here. So we generate synthetic data. How this is done? Yeah, I have an input into my generator model where I do a prediction, and you can imagine when we go through this for the very first time, we have two sources of randomness which act here together. So you see the noise is generated as normal noise. So white noise, it's not scaled whatsoever. And in the beginning, before we have done any kind of training, all the weights in the generator model are completely random as well. So there is no learning, nothing has happened. So for the first iteration, we really have here random input, random weights, and what is coming out there is completely random. So there's nothing learned, trained, given the two-player game, nothing. But after a couple of epochs, of course, this shall change. So then we have the train discriminator, the part where we train the discriminator. The real data is now sampled. It's sampled from the original data. Here, that's the normalized data, right? With the underscore. These days, I usually use the underscore to indicate normalization. And we don't do it for the complete data set. We always do it for 32, 64, 128, or whatever. Batches, not batches. Batches of that size. Here the discriminator, train our batch with the real data. The real data gets the labels once, this is correct. The fake data, the synthetic data, gets labeled 0. So we train here the discriminator on, in a supervised learning context, on what is reality here. Reality, I mean, it knows, it sees exactly what is the correct data and what is the wrong data. And so it learns over time, right? You see, like that's a build, that's correct, okay, I see, then the other one, and so it learns over time. Hopefully, getting better over time, right? To distinguish. And then we train the generator here. again, so this has nothing to do with training, right? So this is training, but we don't start with the training. Here the synthetic data is generated, and here is where the generator is trained, right? Again, with the random numbers as input. And the rest is just output. So print progress every 1,000, you see, this already indicates that usually he would go with a large number of epochs to train the two of them. Right? One point that I might have missed, so sometimes it's that large. I don't see less than when I sit in front of my machine. Yeah, that's here an important point. The in the context of the GAN, the adversarial network, the discriminator is not being trained here in this context, right? So it's not that it is updated when we do the training down here, right? So the GAN here, train on batch. In this particular context, explicitly it is excluded that the discriminator is trained. The discriminator is trained separately, right? In other words, this is, if you like, a ceteris paribus, and everything remains equal from the point of view of the generator, right? So we have the two of them in the GAN, but the weights, to make it a bit more specific, the weights of the discriminator during this training down here are kept constant. Otherwise, because it's part of that model, it would try to change everything, right? So the purpose here is just to train the generator by keeping the discriminator weights fixed. We do the training of the discriminator just before that. So both are trained, but this is an important point here, right? So this means weights are kept fixed. No updating of the weights in any way. So now with the function being defined, here it returns real data and synthetic data. This I have just done for my convenience because I could comment this out and the training would nevertheless happen. I just wanted to have here an easy mechanism to get the last real data set, because this is randomly sampled, so the real data here, this object changes all the time because it's randomly sampled, and the synthetic data is also randomly generated, and I just want to have an easy mechanism to not be in a position where I need to create this all the time, right? So now let's do just one run here. So with regard to the 1,000, not going to 50,000 episodes. That's not my goal here. After 25.8 seconds, we are through. And here you see what I was arguing before. I now have one sampled real data set, one batch, so to say, available, and one created, generated synthetic data set. And I do here a plot of the, what is the batch size? I think 32, I would assume, right? Where did I define the batch size? Here, batch size. Here. It was right in front of me, and I was looking further up. So these are the 32 values. Yeah, when I have a look at this, could you tell without the the legend what is what? And this is like what the discriminator is presented with, right? So here you see, well, this is a high peak. This is too high, but here the order doesn't play any role, right? So whether this peak is here or there, this is not the point, because it's randomly generated. But from the size here, from some, I would say, well, this looks. If this would be a simulation, I would say, yeah, this is generated by the same core, the same engine, right? But of course, this is just us looking at a visualization. So here I now create a data frame with the original data set as input. And here you see I now create over the length of the complete original data set, I create based on noise as before, synthetic data, and do an inverse transform, because I'm going here with the real data. This is not the normalized data, right? If this would be the normalized data, I wouldn't do the inverse transform. But the way I want to do this afterwards, in particular with regard to the returns data to the financial side of things, this wouldn't really work. But I comment on this later on. So I create here 10 random or synthetic, it's not random, it's randomness included, but let's call it synthetic data to differentiate this. And here we see now the statistics, the high-level statistics. Numbers clear. Obviously, the mean value is already well too high. Standard deviation, yeah, it's a different, not that large. The maximum value is quite a bit above, and the minimum, yeah, it's not as low as it should be, right? So when I want to, for example, calculate the mean squared error, right, we get a 1. But a picture, as usual, says more than 1,000 words. And the way I'm plotting this here is that I now do a sorting, right? I emphasized before that here, these are just random values that are generated, right? There is no kind of natural order, sequence, whatever included. I don't do any sorting, but, and that's the reason why I have, this might change maybe if I find some other reasoning and example that I think is better. I've decided to go with an initial deterministic function here, which is monotonically increasing, right? Because then I have an easy time with the ordering. I simply say, give me the lowest value, give me the highest value, and everything in between in order, so that I can, if this would be, I don't know, the square, for example, then ordering wouldn't make sense, right? It would have a completely different mechanism, I don't know what, to sort this. But with a monotonically increasing function, it would also work with a decreasing, but increasing here is the case, right? I have an easy time in ordering. And you see, with this order in mind, yeah, it doesn't look too bad, I would say. On the right-hand side, the neural network gets it much better fitted, right? On the left-hand side, it's not yet that good. This can now have a number of reasons. One major one would be here, 1,000 epochs are not enough. I can, while I'm talk about it, I can restart it here, right? And let it go through it. Or the model capacity is too small. So here, admittedly, it's a simple case, but the model structure already, even for such a simple case, is already quite a bit involved. Right? So as usual, in such a context, we are faced with questions with regard to what are good hyperparameters. How can I optimize them? Can I find better ones, right? So where this is training, maybe it has finished already. Of course, we get here another set. With that one, I would, I don't know. To me, it looks the same. It's too much randomness. for us included. And in particular, when I say randomness, we must keep in the back of our head, or when I say it, you didn't say it, that the real data is not random whatsoever. The sampling is random. But you see here, through random sampling, we can generate something that looks random in the end. Therefore, I bring the structure back here. Let me see. Yeah, the mean value now is much better. Recall before it was well too high. The standard deviation is much closer to the original one. This is now well too low. This is well too high, right? So you see here it is too high. Now, before this was all above here, right? Now it's all below. So we could now go and do it 5,000 times, etc. I think you get the point. Now the financial example. Again, I might better change this to tbq.io. This time correct, the certificate. Yeah, it works. I pick out Apple, could pick out anything else here as well. Right, do the same thing, like instantiate the standard scalar, do a fit transform so that we are dealing with normalized data. Now, of course, I can leverage what I've done before, create generator, discriminator, GAN. So easy and efficient affair. I train the models now over, again, 1,000, that it doesn't take too long for the first one when we sit here and wait. When you are doing this back home and maybe are anyways planning to get a coffee from Starbucks around the corner, then you can let it run for a little bit longer. And I have reduced the capacity here quite a bit. So what basically are we doing here? Just to recap before we now move on. So we have raw data in the form of prices. I pick out Apple. For Apple, I create log returns data. I do a drop NA. I get the values so that I have an ND array object and not a data frame here. I normalize the values, right? And then I train the model here, right? So here the generation you see already takes a little bit, not that long as before, right? But the generation is as before. Noise is drawn over the complete length of the data. Here I do the prediction given the noise, both false is important. Here and this can be debated, so let me do it here as the and I show you the impact. This is usually pretty clear. When we now have a look at the meta statistics here, what do we have? The mean values, they are not too far off, right? Standard deviation, here the differences are larger. Minimum values, also I would say not too far off. The maximum values, it looks kind of okay-ish, right? I'm almost surprised. Here we see now in red the original returns, log returns, and then the synthetically generated returns. This is done here over the complete set, right? And I can now do also an overlay of the sample distribution. Latest here we see, this is not yet that good. I recall our classification case from yesterday. We also had the histogram overlay. It's an easy way here to compare whether the distributions are somehow in line or not. And you see here even the high peak is too far to the right. It's not. It seems to have nothing to do with the distribution itself. And when I now do the same trick like with the sorting, and here I do the sorting with returns, and this also makes sense, right? I can now compare what is the lowest return from the real data, what is the lowest return from the synthetic data, and then I do a cumulative sum, right, time, so that I can visually compare this. Also, this chart speaks, I would say, a simple and decisive language. It's basically not yet there where we would like to have it. And here it shows now that the simulated path, the green, thick green line, this is the average, the mean of my generated time series data set, right? And yeah, this is far off here. And you see also here, yeah, it's going through the roof, too many large realizations, and this is also to be seen here. Basically, the distribution, the sample distribution here is too much, too far to the right. Here the average is roughly 0, and here, it's highly positive. Therefore, we get these, synthetic time series going through the roof. So what can we do? We can, of course, train the model again, doing it in order to hopefully improve the quality. Just looking for something that I'm not sure, but currently it's often when you see something, it's not always that, and the thing that I see might be serious here. It's not always that it's indeed serious. You might be missing something that you have been doing before and thinking and reasoning before. But here I'm just wondering whether in the training part it is working with the wrong data actually. Whether it has still some probably you don't know what I mean. At least it has finished here. Let me try out something afterwards. Now the additional training has actually worsened the situation, right? This is something I have observed a bunch of times now already. I cannot really explain it. You see, it somehow cuts off now at a certain point.
Yeah.
That's what mine's doing, except it on the negative side.
Yeah, and I don't know why it's like, you see. This
Yeah,
is
is it grabbing another rets because it's the rets underscore, and we haven't defined that yet from the new CSV.
I might have, when I copied that stuff, I might have forgotten.
Right there, 37.
I think that is reds, but it trains the model. During this part, I define reds underscore, but the function, the train models function, doesn't reference the appropriate data, right? Because maybe I've commingled here two examples into one. Let me here simply add this y underscore, right? To make it local instead of global, because here this train models function was referencing a global object. So this let me just for some precaution, do this from scratch so that we are not changing the code in a way that the original example is not working anymore. Therefore, I'm executing it from scratch. That one, for some reason it looks now slightly better, at least. Yeah, this was like 1 point something before. Better initialization of the model, maybe. So, and that now. Either I have deleted something or a reference got lost, I don't know. Because in my original notebook I have like also reinforcement learning, agent stuff in between, etc. So I don't know if this is good or not now. This doesn't look too good yet. Let me do one more, but I think it's also a good time to have maybe a morning break. So that I can, during the break, I can let it run quite a bit longer, because what I was saying before, independent of the fact whether there was now a mistake or not, these models usually need to be trained for many, many more epochs than we have now been doing here interactively, right? But that's always a good opportunity when we have a break to let it run for 10 minutes and we don't need to sit here and stare at the screen and hope for the best, right?
I don't have any, well, I have some chips up in the office, but there's some muffins, fruit. Please help yourselves. I can get you a Keurig coffee. Do you accept that? Oh, relative to a cafe.
I'm just trying to figure out because there's the firewall for corporate, so I have to go around it every time.